tak je to Marc Cohen a Mandy Waite a přišli vám popovídat o Google Computer Engineu.
Thank you so much. Dobry večer. Sorry? Marc taught me that. He should get the applause because he taught me that. So, okay, that's pretty much the limit of my Czech. I shall try to do better next time. So welcome everybody. Thanks for coming along today. I hope you're enjoying DevFest. I hope you had a great time today. Unfortunately, as you can see, my Czech is very bad, so this talk is going to be in English. And we're going to talk about building and managing high-performance compute clusters in the cloud. So let's begin. We're just going to set up the technical details here with a clicker. So I'm Mandy Waite. I'm a developer advocate for the Google Cloud Platform. And I'll leave Marc to introduce himself.
Hi, everyone. I'm Marc Cohen. I lead the developer relations team for Google Cloud Storage and Compute Engine out of the Seattle, Washington office.
And you can find more about us at our Google Plus profiles or follow us on Twitter. Awesome. So the agenda today. So what are we going to talk about? We're going to talk about the Google Cloud Platform. How many people know about the Google Cloud Platform? Brilliant. Okay. How many people use things like App Engine? Brilliant. Okay. All right, cool. So we're not going to talk about App Engine today. We're going to talk about Compute Engine specifically. We're going to talk about the resources that it offers in the cloud. We're going to talk about cluster management. And Marc has a brilliant talk and a brilliant demo he's going to go through to talk about cluster management. And then we're going to look at some new features for those people who have used Compute Engine before, but maybe haven't looked at it for a while. And then we'll wrap up with a call to action and offer you some resources you can look at. Marvelous. Okay, so the Google Cloud Platform is an integrated platform, pulls together all of the components that we have for our platform. On the compute side, we have Compute Engine, which is an infrastructure as a service offering. Then we have App Engine, which is a platform as a service offering. Gives you software stacks you can develop your software on. Then we have a storage layer. We have cloud storage, object store, cloud SQL, which is MySQL store, and also cloud data store, which is the massively scalable underlying big table store for App Engine, which is now available externally. Then we have a bunch of services. Then all of this runs on the Google infrastructure. That's the same infrastructure that we use to service your search queries and also to run things like Gmail and YouTube. So Compute Engine. So Compute Engine, as I say, is an infrastructure as a service. It provides resources in the cloud, virtual machines, and other compute resources, which we'll look at in more detail. It's built with Google DNA, so you get the scale, speed, and the global footprint that we bring to the table, and also all of our global expertise and experience when it comes to building massively scalable services and systems. So just a bit of terminology. So we tend to forget this when we talk about projects and zones while we're giving these talks. So some of the terms we're going to use today are the projects, and our cloud platform is split into projects, and Compute Engine also has projects under which you can create things such as virtual machines, disks, networks, and also other global resources such as snapshots and images. Virtual machines and persistent disks are deployed to a zone, and we have 4 main zones currently, 2 in the US, 2 in Europe, and we'll talk about those in more detail later. Then we have these global resources as well, such as snapshots. These are persistent disk snapshots, and we also have things like images, which can be shared across zones. The Cloud Console, I'm going to skip over the Cloud Console demo. If we have time for it at the end, I'll show it to you. But what we'll talk about first is virtual machines. So we have virtual machines in the cloud, Linux virtual machines running either CentOS or Debian, and these run on top of a KVM with a bit of secret sauce. And what we're going to do is kick off a quick demo of spinning up 1,000 or so instances. So Marc's going to do this, and hopefully our network connectivity is going to be good, and this is going to work pretty well for us. So what we're going to do here is spin up 1,000 instances and see how long it takes. So click the button, Marc. And it's grey at the moment. It takes a little while for this to work because it's got to connect to the instances, spin them up. But it shouldn't take very long at all. We have a timer there. So let's wait for something to happen before I go to the next slide. But then we'll go to the slide and skip back to it and see what's happening.
I can say a little bit about what we're looking at here.
Yeah, sure.
So each grid represents one virtual machine out of 1,000, and they're color-coded, so as the virtual machines start going through their stages, we'll see blue, then yellow, then green. And when they're all green, we know they're all ready. So hopefully something will happen soon. This is very exciting.
What happens if they're all red, Mark?
Maybe we'll come back to it. It's a little sluggish.
It is
right
pretty
now.
quick, but it does take a while just to get some of them spun up. So let's go back to the slides and just do one more slide.
Oh. Something did happen. Isn't that cool? Okay, more things are happening. I'm going to restart. Give me 1 sec here. I'm going to restart it, and if the recovery code is right, it'll pick up where it left off, including the timer. So we are getting things going along now. Go back to the slides. Okay.
Okay, so the virtual machines that we offer come with a variety of hardware configurations, mainly a combination of number of cores, amount of memory, whether they have a scratch disk or not. And we have standard instances which come with a certain amount of cores, a certain amount of memory. Then we have high mem instances that obviously are suitable for workloads that have a much higher memory requirement. Then we also have high CPU, which where the focus would be on the CPU performance as opposed to memory. We also have shared core instances, G1 small, F1 micro. These are shared across a core with other virtual machine instances of the same type. And they're pretty good. They're very cheap to run. So you can use these for testing, spinning up clusters, the kind of thing we're doing with a quick start. And they all run CentOS or Debian Linux, and all the M1 instances have dedicated resources. They have dedicated cores and dedicated memory. It's not shared across instances. And you pay for only what you use. So we don't bill by the hour, it's sub-hour billing. We bill by the minute, 1 minute granularity, and you pay for 10 minutes minimum when you spin up an instance. So that's pretty good, and that means you only pay for what you use. So in terms of storage, these virtual machines need something to boot from, so they need some kind of block storage device. Well, we have a scratch disk offering that makes a lot of sense when you're bringing machines up, but we also have this persistent disk storage, which I want to talk about in more detail. And persistent disk is effectively attached storage, network attached storage. It's used for long-lived data, and you can have a number of possible use cases served by this particular type of disk. We have the root disk option. We have a read-write data volume attached to an instance, and this can be attached and detached as needed. It can be attached to any instance within the same zone. And also we can attach it to multiple instances in read-only mode. So that's what we have here. Do you want to go back to the quick start, Mark? Otherwise it will finish and it'll just look like a screen capture. Okay, so we'll run this again during the Q&A session, just so you can see it happening while it's going. But that's all of the instances spun up, and it took 1 minute 24 seconds. Is that a new record, Mark? So that's the quickest we've ever done it. So like the 1:30 we hit at the Velocity conference, but that's the fastest we've ever seen it do it. So 1,000 instances in 1 minute 24 seconds, which is pretty cool. Okay, so persistent disk architecture, these are virtual volumes, so they are made up of disk blocks across many physical devices, and the data is copied across many physical devices and also across data centers as well for high availability and reliability. This data is encrypted in flight and at rest, and for resiliency, we make multiple copies of that data. That makes it very resilient, and also is fundamental to one of our consistency parameters that we have. We also use these checksums, HMAC checksums for disk data. So when we write data to a disk, we calculate a checksum and write that along with it. So when we make the read on the data, we compare it with the checksum, and if it's incorrect, we return no data. Performance characteristics, we have random write optimizations that give great performance, no hotspots. And also we have this last feature, which is the most exciting. All the copies that we make of the data are equal. There's no primary copy and some backup copies. They're all equal. So What we can do when we want to read a block is say, give me all the copies. We go to every copy and ask for them. Then we get back the fastest one and we use that. Then we ignore all of the rest of the gets that we did in the rest of the data. That means we use the fastest copy every time, and that means we avoid hitting a hot disk or anything like that and increasing latency. So networking, we need to connect these virtual machines together. So that we have some the fairly fundamental things that you need when you're networking. Firewall rules, by default, everything is blocked apart from the SSH ports. So if you want to do things like HTTP requests or Redis, you need to open those ports up. We have routing for setting up things like virtual private networking, advanced networking features. Then we have load balancing, which has forwarding rules and health checks, and instance pools that connect to these forwarding rules, and of course instances themselves. Then we also have connectivity to the internet. And finally, in my part of the talk, I want to talk about the APIs and client libraries. So everything in Google is pretty much an API, and Compute Engine is exactly the same. So we have an API, and on top of the API, we have a bunch of client libraries, written in many different programming languages, I believe 12 at the last count. Our tools, our GCU tool is built on top of that. That's the command line tool. Marc will probably mention that later. The Cloud Console, which hopefully we'll get a chance to give you a quick demo of, also uses that API and the client libraries. And our third parties, the third parties we work with, again, we're going to talk about some of those later, but they make use of our API to build their own tools. And of course, you can use the API to build your tools. You can build tools to facilitate management of resources, or you can build the whole creation of resources and tearing down of resources into your own workflows. And with that, I'm going to hand over to Marc, who's going to talk about cluster management.
Thank you, Mandy. Good. Dobrý večer. Not surprisingly, nemluvím česky. However, tak si budu mluvit anglicky. And that completes my remarks in Czech for tonight. Not so sure. Thank you. You're very kind. So I'm going to talk about building clusters on Google Compute Engine. So we just showed you how fast it is, how responsive it is. And I want to kind of get into a little bit more practical level and talk about some examples of code where we actually play around with cluster building. Is the audio kind of loud? It sounds loud to me. Is it possible to turn me down a little bit? Just so it's not quite so overpowering. I can pull this back a little bit too. So I'm going to sort of tell this story through an app that we'll walk through together. And I always like to write my requirements before I start coding. Not always done that way, I know, but these are my requirements for this sample app that we're going to look at now. So I wanted to do something interesting rather than just create a bunch of VMs and just say, look, there's a bunch of VMs. I wanted to actually make it do something fun. I wanted to build it entirely with open source software, which is driving a lot of the ecosystems nowadays. I was really interested in making it self-configuring. A lot of the problems you have with clusters, like the ones you might build with Compute Engine, have to do with creating more than one or two of them. It becomes a lot of work to keep them in sync and to manage them, and making them self-configuring where you create new nodes and they just kind of immediately become part of an application is really valuable. And I wanted to make sure the cluster was independent of lifecycle management and the underlying computing environment. So what do I mean by that? I don't want the application to force you to use a particular tool to add nodes to the cluster or to remove nodes from the cluster. It should be agnostic. And ideally, the cluster could be hosted anywhere. It doesn't have to be in Google Compute Engine. So the next most important job after defining your application requirements is to pick a cool name. And the one I chose for this application is perfuse, which means to permeate or suffuse something. And I think that captures a lot of what this application does, because it's about performance testing. So the notion is that we're going to have a server node and a bunch of slave nodes. And with a web UI, a very simple web UI, we're going to send performance test requests to the master. The master is going to turn around and send those requests to all the slaves, and then get the feedback in terms of how the performance ran, send the results back to the client web app, and then we'll graph it dynamically. So that's a mock-up of what it'll look like. I said I like to use open source software, so these are the building blocks that I chose. Angular and D3 for the kind of templating framework and visualization respectively. I'm using Node.js and Express on the server side. No reason other than that I kind of like it. I've been interested in it for a while, and I like the environment of being able to use JavaScript in both my client and my server. I'm using WebSockets for the dynamic updating of the client in the actual web app, and I'm using 0MQ for farming out the fan out of the performance tests on the server. And then lots of different tools are available on instance creation. I'll talk more about those shortly. And then we'll talk a little bit about snapshots and Docker and how we kind of deploy things with this application. So this is kind of a pictorial view. The browser's running some JavaScript code. It pulls a page from the server, from the same server that's serving WebSockets. Based on the user requesting a particular type of test, it'll send the request over WebSockets for the test to run. The server will, or the master will fan that out using 0MQ to all the slaves, get the results back, and again, using WebSockets, give the results of the whole group of tests to the client. So I thought it was interesting that in order to do all that, not that that's the most impressive app in the world, but it's interesting in the sense that it's distributed, it's dynamic, self-configuring, has some nice visualization characteristics. With all of that was on the order of 500 lines of code, and I think that's partly that way because of things like Node and 0MQ that give you a really nice high level of abstraction for free, essentially. So I think it's a testament to the quality of the open source ecosystem. I'm going to now just take a quick walk through some of the code I used to put this application together. So on the master server, which kind of comes up first, it opens up a WebSocket port, and then this code here is express.js, which is opening up a conventional web server on port 80 just so that it can serve the initial page index.html. The master also opens connections for 0MQ. So there are two types of connections here. One is a pub sub, and this is telling 0MQ I want to be the pub side, the publish side of a pub sub socket, binds to it, and then it also has a pull socket that it opens a connection to. And the slaves are going to set up kind of a mirror image to that configuration. So they come along and they set up the sub side of the pub sub, and they set up a push that's on the other side of the pull socket that we just looked at. So if you haven't seen this before or worked with 0MQ before, it's really a nice high-level environment with which to do a lot of sophisticated networking like this. So really worth taking a look at if you haven't played with it. And then this is basically this is making the connection from the slave to the master for the push-pull. So this is for the push side. And then this is essentially doing the same thing for the pub sub socket. This is officially starting to subscribe to the pub sub. Then we jump, so that's kind of everything that the client or the master and the slaves are doing to get everything ready to go. Then we have a web page that comes down. It's trivial, I'm not showing it here, but it basically gives you a couple of controls and the ability to select a test and say, run my test, please. That comes through, when you click test started, the request comes through with a WebSocket request. This is the client configuring that WebSocket request and sending the test. And then it's using JavaScript to repeat that test request every so many seconds. This is back to the master, which receives the WebSocket test request. It logs the fact that it got that request, and it sends it to the clients. Now this looks like it's sending it to just one client, but this is the pub side of the pub sub connection. So when it does this one simple send, it's actually fanning out right there to any number of client or any number of slaves. Sorry, I keep interchanging client and slaves, I think. But that's going out to all the slaves in the cluster. And the nice thing about this is It's sort of stateless in the sense that the server doesn't need to keep track of or care how many slaves are out there. It just sends to this pub/sub connection, and however many slaves are part of the cluster, they'll automatically get notified and be able to run those tests. The slaves basically say something like this: whenever I get a message on the sub side of the pub/sub, that's the sock receive, run the command that corresponds to that message and send the results to the push side of that push-pull connection we just looked at. The other side of that push is this code on the master, which says whenever I get a message on that push-pull socket on the pull side, I want to send that to the WebSocket connection. So that's just taking those results and sending them down to the UI in the browser. And then likewise on the browser, there's trivial logic here, which is saying whenever I get a result from the WebSocket connection, use it to update the bar charts. Finally, this isn't really part of the app, but I wanted to show one example of how to add nodes to the cluster or take nodes away. So this is a simple shell script that is embedding the tool we use for Compute Engine to give you a command line capability for creating virtual machines and deleting them. So this has a simple start and stop syntax, and it's just giving a very thin layer over gcutil add instance to create a sequence of VMs and delete instance to remove them. So let's take a look at this in action. So I have, if I can find my shell window here. gcutil list instances simply does the API to get an inventory of all the virtual machines running right now. And it should give me a list of all the instances. I have one master and 5 slaves running right now. And that's taken a little longer than I would expect. So rather than have you watch this go slowly, I'm going to switch back to the demo. And the first test I'll run is called random. And so what this is doing is just asking the slaves to generate a random number, and it's doing this test every 3 seconds. So this is just showing you that there actually are live virtual machines in this cluster, and they're actually receiving the requests, doing the performance tests, sending them back, and the visualization's actually working as we would like it to. So here's the results of my gcutil list instance, and now I know why it took so long. That little demo we did earlier with the 1,000 VMs, it had to go out and get, it doesn't just get the name of the VMs, it gets kind of a nice programmatically effective JSON document for each one. So it had to download a bunch of stuff to capture all those thousands of VMs. So what I'm going to do now is just show you this. I talked earlier about this notion of you want to make it really simple for nodes to join the cluster and just kind of appear out of nowhere and be effective. And so I'm going to use that script I just showed you. I'm going to say start. Right now we have 1 through 5, so I'm going to say start 6 through 10. And we'll jump back to the demo. And what that should do, let me make sure it's starting okay and it's not unhappy. Okay, so it's starting those guys. And what that's doing is calling gcutil add instance with kind of a pre-configured setup to make those new VMs run like slaves. And you see 8 and 10 just came in, 6, 7, 8, 9, 10. So all 5 are there now, and you notice they're doing something, right? They're actually running the same tests that the rest of the cluster is running, giving me the results. The client code, the server code, the slave code, none of it had to be told. I didn't have to go and administer anything. The mere presence of the cluster, of the new VM in the cluster, kind of just automatically, seamlessly was able to contribute to the function that was going on here. So I think that's a really nice kind of design goal when you're designing your own clusters. So I said that at the beginning that I wanted this application to do something interesting. And I think it might be a stretch of the word interesting to say that I've achieved that, because you know, the bars are dancing around, that's nice, but they're just random numbers. So I also have the ability to actually run real tests. So each one of these virtual machines has a persistent disk attached. Mandy told you about those. These are network attached, very high performance storage devices. So I'm going to do a rand read. And this will do an FIO command. This is showing you the command it's actually farming out to all the slaves. But this will do an FIO command which will measure the performance of random reads on the persistent disk on every slave in the cluster. And it's a little bit choppy initially, but it kind of settles down. And the message here, the key takeaway here is that we put a lot of effort into making these persistent disks consistent and predictable. One of the problems in cloud computing is that you might get a virtual machine every once in a while that doesn't work as well as your other virtual machines, or you might get some disk resource that's giving you some performance problems. We've really tried to make our persistent disk, as well as many other aspects like our networking, as consistent as possible, and that's kind of what this bar chart is showing you. It's pretty flat and pretty consistent. Keep losing my place here. Let's see. Here we go. Okay, a couple other items. So that's the end of the demo. And clicker battery is dead. Back to the keyboard. Oh, maybe it's because the window's not selected. Let's try that. That helped. Okay, so I created the slaves in that cluster using a command line tool. Could I have used something else? And the answer is yes. We have partners like RightScale and Scalar who, that's their primary business, is to create nice tools to make it super easy to anticipate traffic demand and dynamically grow and shrink your clusters as needed. But there's a bunch of open source projects out there that also come into play here, which are very nice projects in their own right. You can get involved in these projects and try them out yourself. And we've made a concerted effort to try to make sure those projects work well with Google Compute Engine. So we actually have a project that just is focused on adding plugins and soliciting help with these open source products. So Chef, Puppet, Vagrant, Ansible, and we're working really hard on getting SaltStack and Docker working well with Compute Engine as well. How am I doing on time? 15 minutes, and you probably need about 5 or 10? Okay. So popping up a level, I wanted to talk a little bit about deployment. So I kind of showed you an example application, and we talked about making it dynamic and self-configuring all that good stuff. How did I actually deploy that code? There's some nice tools in Compute Engine that come into play in this space. For example, one way you could do it, this isn't the only way, but the way that I actually did the work for this app was I had a model VM. And the model VM was kind of my prototype where I staged all my software and did all my testing. And I had a model PD, persistent disk. And every once in a while I would generate a snapshot. So as Mandy said earlier, a snapshot is a copy of everything on the persistent disk at that instant in time. And it's a global object. So you can use that snapshot to clone that disk image, or to back up the disk image, or anything you like. I used it to essentially seed the complex that I'm creating. So when I actually create a production cluster, like the one I did with that shell script, I just told it to use the same snapshot. And the way I didn't mention this, but the way it figured out, like when I start any arbitrary VM, the way it figures out whether it should behave like a slave or a master is currently hard-coded into the name of the master. We could make that more dynamic and do all sorts of cool things with that. But anyway, the snapshot and PD mechanism is very powerful for deploying code fast. But one bad thing about it is that in order to deploy a new cluster or a new node in the cluster, I have to start the node. And if I want to change the code on that node, I have to stop it, destroy it, and start a new VM. That's kind of a heavyweight operation to just try some new code. So a nicer model would be a lightweight container such as Docker. And I've been playing with Docker just recently. It's a really nice way to do this deployment where you can package up all your dependencies, all your runtime objects in a Docker image, and have the VM just pull it on demand to deploy your code more dynamically. So the VM just keeps on running, and you don't have to destroy anything or restart. And I think the best of both worlds, it is nice to have the snapshot that you can boot from really fast and be ready to go. But the iterative nature of Docker is a great advantage as well. So I think the best of both worlds is to combine those two approaches. And over time, I think you'll see that the things that are less volatile and changing the least in the Docker images will probably migrate over to your snapshot or your AMI if you're using AWS. A few best practices I'll just go over really quickly. Automating everything is really important when you're building these sorts of production clusters. You want to manage your configuration artifacts, ideally using declarative statements, syntax, and you want to manage that declarative statement like it's code, using source code repositories and things of that nature. You want to prepare for maintenance events and outages and test your backup and recovery procedures. A lot of people test the backup. Not everybody tests the recovery. It's a lot of work, but it's really important to make sure your clusters survive outages. Reliable systems are built on great infrastructure. We think we have a great infrastructure for you in Google Compute Engine, but also great application design. We don't design the applications for our customers, they design them themselves. So I think building your applications for reliability and robustness is really a key thing that you should be thinking about early on in the application design phase. And then finally, people. This is an often neglected part of the equation, but training people and having great human processes around building your clusters, deploying your code, and recovering from outages is really, really important part of the picture as well. We talked about self-configuring VMs. The last point I wanted to make is that Google offers, along with Compute Engine, lots of other managed storage or managed services, as Mandy alluded to, like Google Cloud Storage, Cloud SQL, Cloud Data Store. These are all really nice services, not just because they're technically great, but because they have a lot of managed capabilities built in. They automatically grow and shrink as you need. They can serve ridiculous scale requests very quickly. So instead of, you're completely free to build a cluster and deploy your own MongoDB database or Redis cluster. But it's also worthwhile taking a look at some of these managed services to see how you can get a lot of the administrative overhead for free. And with that, I will turn it back over to Mandy.
Okay, cheers, Mark. So new features. I think we're going to talk about just one new feature. Give you guys time to ask questions. So we're going to talk about transparent scheduled maintenance. So we like to keep our zones patched and up to date, and we like to repair them, clean them out, find the rats and the mouses that have been hiding away in the server systems and all of that kind of thing. Generally clean them up, patch them, bring them up to speed. And the way we used to do that was to take them offline. So we would take an entire zone offline for 2 weeks, every 20 weeks or so. And if you had resources in those zones, you would have to move them manually yourself to a different zone during that period. So now what we've done is we've changed that, and we've rolled this out in the US, and we're going to roll it out in Europe next year. But what we do now is we take part of the zone offline, and it may be a part with your instances and resources in. And we call that a scheduled maintenance event. And what we do is transparently move all of your instances and your disks to part of the zone that's not affected by the maintenance event. And that pretty much doesn't really interrupt them. It interrupts them a little bit. There may be some workloads that are sensitive to that kind of movement, but for the most part, your application won't notice that they've been moved from one place to another. We do have the option to take them down for you as well and bring them back up again in the same as they were before. But transparent maintenance is pretty crazy because it just moves everything for you and you won't even notice it. We think we can run these machines for a very, very long time, Marc. Yeah? So we have a project called Methuselah going on that hopefully will test that. We can see how long we can run virtual machines in a zone without ever touching them, without them ever going down. So that's really great. And that's the only new feature I'm going to talk about today. That will be rolled out in Europe next year. And we're going to skip ahead. Load balancing has some new features. Differential persistent disk snapshots means you only pay for a difference between one snapshot and the previous one, which can be a good time saver, saving performance and also save on cost. But next, we're going to talk about a call to action and resources. So these are the key takeaways. We think the Compute Engine is extremely powerful. Thank you. Extremely powerful and is very, very fast. It's perfectly suited for the kind of self-managing high-performance clusters that Marc was talking about. Built with Google DNA, scale, speed, security, and all of the knowledge that we bring to the table when building those systems. We're also very committed to making Compute Engine work very well with open source software and the kind of stacks that Marc alluded to. Vagrant, currently Ansible, SaltStack in the future, Docker. And if you want to kick the tires with the platform, if you want to use the platform, you can go to cloud.google.com and find out more about the platform. We also have an offer for credits as well, so we'll give you $2,000 worth of credits. If you go to this link here, short link is BC1SA, capital B, capital A. And if you enter the promo code MWA in, we can give you $2,000 worth of credits. $1,000 for App Engine and $1,000 for Compute Engine. Sure.
1 second for people to jot that down. I see some people are interested in that. So it's cloud.google.com is the website, /starter pack, all one word. And if you enter in this magic code MWA-IN, you will be able to avail yourself of a $2,000 credit for the Google Cloud Platform.
That kind of allows you to really kind of kick the tires of the platform. Compute Engine, cloud storage, cloud SQL, all of our cloud services. And with that, I think we're pretty much done with the talk, so let's answer some questions. Anybody have any questions? It seems like it's very difficult to pass the microphone around, so we'll repeat your question when you ask it. Any questions? Hey, hello. Okay. So the question is, what is a snapshot, the snapshot we've been referring to throughout this talk?
Yeah, it's a disk image. It's a copy of a disk image in time, and with the differential snapshots feature, it's an incremental copy. So each time you take a snapshot, you're storing and paying for what's changed since the last snapshot you took, but it's only for disk storage, and it's for a specific disk. So if you have multiple PDs, you're going to have a whole train of snapshots for each one.
What it kind of allows you to do as well is it allows you to build new disks from the same image. So if you want to make a copy of a disk, particularly a boot disk, you can make multiple copies of it and bring instances up with it. It allows you to move data between zones. So you can create a snapshot of a disk in one zone, say in the US, and bring it over to a zone in Europe. There's several use cases that snapshots are perfectly suited for.
Right, and PDs have interesting use cases as well. Like you can mount a PD in read-only mode, and in that configuration, you can use your persistent disk as essentially a distribution point for static content throughout fairly large numbers of VMs in a zone. But that disk is kind of centered in that zone, and it can't be mounted in another zone. So the snapshots gives you that extra level of indirection where you could make a snapshot, load a disk in another zone from that snapshot, and do the same trick of mounting that read-only in the other zone from a bunch of VMs. Did I see a hand over there? Okay.
Any more questions? GPU. So GPUs. The question is, do we plan to offer GPUs for our instances? Yeah?
Yeah. So we've definitely heard that request from a lot of people, and we're looking at it very hard, but I don't have anything that I can share specifically today.
It's a very popular request, definitely. Any more questions? Okay, so...
We will be here for a little while afterwards, so if you have a question you didn't want to ask in a big room, feel free to come up and talk with us. Thanks for attending today and for your attention.
Yeah, and enjoy the rest of DevFest.